Welcome back to the next video, everybody. Today, we're going to begin taking a lot of the information we've learned over the past several videos and start pushing it back towards conjecture 1 and the concept of modularity. So today, we'll be looking at the Euler factors of the abelian variety AF attached to a new form or a primitive form, if you like, F. Okay, so let's recall conjecture 1. Take an abelian variety A over Q. Let's let lambda of AS be n of A to the S over 2 power, where n of A is the conductor of A, times 2 pi to the negative s gamma s all to the g power times L of AS, where L of AS is the L function of A. We conjectured that lambda of AS has an analytic continuation to an entire function that has functional equation lambda of AS equals W of A, lambda of A 2 minus S, where W of A is called the root number of A. Okay, so this would be a big deal if it was true. It would mean a lot for the theory of abelian varieties in general, and we could do much more with the L function. Okay, so let's take AF now, specific abelian variety AF attached to a primitive form F, and let's look at its Euler factors, its local L functions at primes of good reduction. So theorem 8, let's let F be an S2n chi. Let's let it be a primitive cusp form of level n with Fourier expansion F equals sum over n at least 1 A of n q to the n. If P doesn't divide n, then we know A sub F has good reduction at P. And so it turns out that P sub P of AFT, the Euler factor or the local L function of A sub F at P, has an explicit, very nice formula, in fact, an Euler product, given by the product over sigma of 1 minus A of P to the sigma, or sigma acting on A of P, times T plus chi of P to the sigma, or again, just sigma acting on chi of P, times PT squared. And this product just runs over all the distinct embedding sigma of the number field K sub F attached to F into C. Okay, so this uses the previous proposition from the last video. It also uses theorem 4 from the chapter. It uses some neat linear algebra, a theorem of Ribbit on the finiteness of the torsion subgroup of points of an abelian variety over the maximal cyclotomic extension of a number field, and the Chebytarov density theorem. So lots of high-powered stuff. This is all taken care of in CSS page 92. Okay, so we have a formula for the local L function attached to A sub F if F is a primitive form of level n at primes of good reduction. We already took care of primes P not dividing n, so the primes of good reduction. Let's let F be a primitive cusp form of level n in S2n chi with the usual Fourier expansion with coefficients A of n. Take a prime P now that does divide n. And let's define P star P of AFT to be the product over sigma of 1 minus A of P to the sigma times T. So it's almost the same thing as P sub P of AFT for primes P of good reduction, but we get rid of this last term here. And what you should think of this star notation for the rest of the slide, you should think of that as meaning this right here, whatever I define this to be, is a good guess for what I think the quantity without the star should be based on theorems and facts I already know. So in other words, I think this is a great guess for the local Euler factor, the local L function attached to AF at the prime P dividing n. And so I'm going to put a star here to indicate that. Okay. Let's let G be the degree of the number field KF over Q. Let's let n star of AF be n to the G. So again, this is a great guess for the conductor of AF, so I'm putting a star here. Okay. Let's let W star of AF be the product over sigma of W of F to the sigma. Again, this is a great guess for the root number of AF. Take the product of the root numbers of all the F to the sigmas, where sigma runs over all the embeddings of KF into C. Okay. And let's set L star of AFS to be the product over sigma of L of F to the sigma S. Again, a great guess for the L function of AF is just the product over sigma of all the L functions attached to all the various F to the sigmas, as sigma runs throughout all the embeddings of KF into C. And finally, let's let lambda star of AFS be n star of AF, all to the S over 2, times 2 pi to the negative S gamma of S, all to the G, times L star of AFS. Again, if you were to remove all the stars here, this left right-hand side would be a great guess for what lambda of AFS should be based on conjecture 1. If you trace back through definitions and notations, you find that lambda star of AFS is nothing but the product over sigma of lambda of F sigma to the of F sigma S. Okay, so AF and conjecture 1, what's going on here? We know from proposition 14 in a previous video that each lambda F to the sigma S has an analytic continuation to an entire function of order 1 with functional equation lambda of F to the sigma S is W of F to the sigma lambda of f to the sigma rho 2 minus s, where rho is just complex conjugation. So this was a proposition we already had. Okay, so the thing though is if you compose with rho, you're just permuting the distinct embeddings of kf into C. And so you find that lambda star of AFS also has an analytic continuation to an entire function of order 1 with functional equation lambda star of AFS equals W star of AF lambda star of AF 2 minus S. You have all this already. Okay, in other words, AF just about satisfies conjecture 1 from the first slide. Okay, but what's missing? What's missing is I don't actually know that L star is the L function of AF. I don't actually know that N star is the conductor of AF. And I don't actually know that W star is the root number of AF. Okay, so here's the wild theorem then. A consequence of, you guessed it, Carriol's-Hard theorem popping up all over the place, is that it turns out the local Euler factor, the local L function of AF at T is the product over sigma of 1 minus AP to the sigma T for P dividing N. It turns out the conductor of AF is N to the G, and it turns out the root number of AF is the product over sigma of W of F sigmas. So we have the following. Let F be in prim 2N, and let G be the degree of the number field KF over Q. Then L of AFS, N of AF, and W of AF coincide with the product over, with L star of AFS, N to the G, and W star of AF. If you go back and look at our notation, where sigma runs over, as usual, the distinct embeddings of KF into C. In other words, actually, AF isn't just close to satisfying conjecture 1. It does satisfy conjecture 1. Huh, interesting. So the abelian varieties attached to primitive forms satisfy this amazing conjecture where they're essentially, more or less, their L functions analytically continue, which is crazy, and it makes their L functions so useful, and have a beautiful, simple functional equation relating values at S to 2 minus S for any S in the plane that you like. Interesting. Let's bring this all back together and push this all back toward the concept of modularity. Let's let prim 2 be the union of all the sets prim 2n as n ranges over all the natural numbers. And let's let A over Q be any abelian variety. If A is Q isogenous to a product of abelian varieties of the form AF, where F is in prim 2, then we'll call A modular, a familiar definition generalized to abelian varieties from elliptic curves. We have seen for elliptic curves at least, but it's true for abelian varieties, the L function conductor and the root number of an abelian variety A depends only on A up to Q isogeny. Okay, and it turns out that all three of these quantities respect products as well. For example, product of conductors is conductor of the product, and same for root numbers and so on. This is all basically Carriol's theorem. Okay, hence this discussion on this slide plus the theorem above immediately gives us the following. Let A be any modular abelian variety, then A satisfies conjecture 1. Proof, products respect everything, and modular abelian varieties are products of A sub F, and A sub F already satisfies conjecture 1. Okay, so we are going to dig a little bit deeper into this over the next couple of videos, which will allow us to finally conclude chapter 3 of my notes. And so thanks for watching, and I'll see you then.